Thank you very much for that kind introduction, Professor Chu. I must note that Professor Chu is also one of the leading investigators in this emerging field of biogeotechnical engineering. And so I was flattered, I was honored to be asked to make this presentation, which I understand is the first one in the Center for Urban Solutions Biogeotechnics online seminar series. So in case some of the listeners are new to the field, I thought I would start out, since the title of my presentation is Bio-Mediated Geotechnics for Hazard Mitigation, Environmental Protection, and Infrastructure Construction, with a little explanation of what is bio-mediated geotechnics. And it's one component of this emerging sub-discipline within geotechnical engineering, of biogeotechnical engineering. And biomediated geotechnics addresses processes managed and controlled through biogeochemistry. It's a companion to bio-inspired processes. That's the second half of biogeotechnical engineering, in which biological principles and materials are employed to develop abiotic solutions. These are somewhat different or disparate processes, but they're linked by a common premise. And that premise, that biogeotechnical premise, is that through 3.8 billion years of trial and error, call it evolution if you want, or trial and error, or intelligent design, nature has developed many elegant and effective biogeotechnical processes. So we can learn from nature how to use these processes to address a variety of geotechnical problems. So for instance, this is a building in San Francisco called the Cliff House. And I think it's obvious why it's called the Cliff House. Those cliffs are carbonate cemented sands, bio-cemented sands that naturally formed. And from an engineering perspective, are very resistant to erosion. From a geological perspective, maybe not so. But from an engineering perspective, you know, they're durable materials that are very resistant to wind and water erosion. Here's a picture of a seed that's germinating. And when that seed germinates, it sends down a root and it sends up a stem with much greater efficiency than we penetrate the soil, and that within which we resist lateral loads on that stem. So what can we learn from that seed to enhance our penetration processes or our foundation systems? And this is a picture of an ant tunnel. Some of you may have had an ant farm like this when you were children. The ants tunnel 2 orders of magnitude more efficiently than people in terms of the amount of energy they use to move the earth. Now, we'll probably never get to that level of efficiency, but what can we learn from ants and how they tunnel to make our tunneling processes more efficient and safer? Ant tunnels are very safe, and the ants can detect what sand grains they can remove without causing the tunnel to collapse. If we could understand how they could understand that, we could tunnel much more safely in fractured and blocky rock. So back to biomediated processes, which is the topic of my lecture today. So mediate, that's a verb in the English language, to bring about as a result of some physiological effect. So biomediated geotechnical process is a biogeochemical reaction that changes the geotechnical behavior of the soil or rock beneficially in a way in which it can aid us in our engineering. And it may involve a living organism like a microbe or a fungi, or a biological material like an enzyme. Sometimes we broadly interpret this process to include abiotic natural processes, interpreting the word bio as in the biosphere. So any process that's in the biosphere, even if it doesn't involve biological materials or a living organism, we might interpret as a biomediated process. And we can argue about that forever. I think it's up to the individual as to how they want to interpret that. So this is a little diagram prepared by my colleague Jason DeYoung that illustrates why we are interested in biomediated processes from a geotechnical perspective for improving the properties of soil. So we have a chemical reaction that may induce inorganic precipitation. We call that biomineralization. It could induce organic precipitation, biofilms, gas generation, biogas, and all of these processes can have beneficial engineering effects. And all of these processes can be controlled. They can be mediated by biological reactions, by providing nutrients, by stimulating microbes. We can mobilize these chemical reactions to influence the mechanical properties of the soil, to influence the permeability by 3 orders of magnitude, to influence the stiffness by 2 orders of magnitude, compressibility by 2 orders of magnitude, shear strength by 2 orders of magnitude. We can control the volumetric response to some extent. We can do these pretty well in the laboratory right now for a variety of processes. The challenge in front of us now is upscaling these processes from the lab into the field. And the field, when we apply these processes in the field, we have to deal with issues like spatial uniformity of the ground and the permanence of our processes. And we're really just starting to address those issues from a biogeotechnical perspective. So beneficial biomediated geotechnical processes include mineral precipitation. And by precipitating minerals, we can cement soils together and increase their strength and stiffness. We can sequester contaminants in the soil. We can densify the soil and make it more dilatant. We can reduce the permeability of the soil. Biogas generation, and we can take advantage of that to reduce the permeability of the soil or the hydraulic conductivity, because the unsaturated hydraulic conductivity is much lower than the saturated hydraulic conductivity. We can change the undrained behavior. And I put undrained in quotes because typically when we think of undrained behavior, we think of a saturated material which doesn't change in volume. But when we desaturate the soil with biogas generation, even though the soil is undrained, it may still involve volume change. And we can take advantage of that in some situations, for instance, in mitigating earthquake-induced soil liquefaction. We can also use organic precipitation to generate biofilms. We can use that to reduce the permeability. An interesting application that we've talked about in my center, but really haven't addressed in full, is corrosion protection. You know, dentists are using biofilms to prevent cavities in the teeth. Can we use biofilms to prevent corrosion of steel elements buried in the soil, piles and pipelines? And then we have chemical transformation of chemical species. This is a process that's widely used now for soil and groundwater remediation. I'll talk a little bit about that at the end of the lecture. So what I'll talk about today will be mineral precipitation. It's the most investigated biomediated process. And carbonate precipitation is the most studied mineral precipitation process from a geotechnical perspective. And we have MICP, microbially induced carbonate precipitation, and that's the most common process people are looking at. EICP, enzyme-induced carbonate precipitation, is also popular. It's coming on fast. And then there's a third process that we call MIDP, microbially induced desaturation and precipitation. That is also an investigation primarily for desaturation, but also has some benefits in terms of precipitation. Now, there are many other mineral precipitation processes involving iron, phosphorus, salt, and other minerals, but carbonate precipitation is still the one that has generated most interest among geotechnical engineers. So, calcium carbonate precipitation. I call it bioalchemy. I call it turning sand into sandstone via precipitation of calcite or calcium carbonate as calcite as bioalchemy. You know, the medieval alchemists, they wanted to turn lead into gold. Well, we're not turning lead into gold, we're turning sand into sandstone. But if we can do that efficiently, cost effectively, we can make just as much money as we could make by turning lead into gold. Hence the term biogeoalchemy. One of the first students I had working on this process, Ismail Karadas, identified 7 different natural processes by which calcium carbonate is precipitated in nature. One of them, for instance, is the White Cliffs of Dover This isn't carbonate sand. This is pure carbonate that was precipitated by a geological process. Again, these cliffs are very erosion resistant from an engineering perspective, from a 75 to 100-year lifespan, perhaps. Maybe not in geologic time, they will erode, but from an engineering perspective, this carbonate precipitation has created a very durable material. And so if we could learn how to do that where we needed this kind of material, that would be a great contribution to geotechnical engineering. Here's my friend the Cliff House again. The west coast of California has these weakly cemented sandstone. They're called weakly cemented by the geologists. From a geotechnical point of view, they're sometimes pretty strongly cemented. All the way up and down the coast of California, from the California-Oregon border in the north down to just north of Los Angeles in the south. Again, they're resistant to earthquakes, resistant to liquefaction, from an engineering perspective, resistant to erosion. We also have anthropogenic carbonate precipitation processes. Down here on the lower right, this is a picture of leachate gravel from a landfill that's been biocemented by precipitation of calcium carbonate. And in the landfill business, this is not a good thing. This clogs up our leachate collection systems. But I first got interested in this, or I first got interested in biogeochemical engineering when I was exposed to this, and I thought, well, in a landfill, that's not a good thing. But what if we could get this to happen in a situation in which it's beneficial, for instance, under a building or in an area where we wanted to tunnel through cohesionless sand and gravel? It turns out the process that creates carbonate precipitation in landfill drains is not really suitable for geotechnical purposes. It involves methanogenesis, and we don't want to be generating an explosive gas that's also a major contribution to global warming. But it started me thinking along the track of maybe we can biocement soil for engineering purposes. And here's another anthropogenic or human-induced mechanism. You know, we often see white scale on pipes around the joints where they leak a little bit. We see these scales on the inside of pipes. And these are typically calcium carbonate scales that develop in a relatively short period of time, a time frame that would be suitable for engineering purposes. So if we can control calcium carbonate precipitation in sands and cohesionless soils, there are just so many applications. We can support foundations without piles, with smaller footings. We can control fugitive dust. You know, we first looked at fugitive dust as kind of a side application at construction sites. Frankly, of all the applications that we've been looking at in our center, this is the one that has the most interest from outside parties, and I'll talk quite a bit about it later. Mitigating earthquake-induced liquefaction is something that's very dear to my heart, having lived in California for 20 years. We could stabilize underground openings in what our tunneling colleagues call running or flowing sands. We could stabilize subgrades for roadways, stabilize slopes. We could provide surface water erosion control, scour protection around bridge piers. We could create building materials, biobricks, by biocementing sand and gravel. And there are many more applications. I think you just have to use your imagination. So let's talk about the three predominant processes that people have looked at for carbonate precipitation, starting with MICP, microbially induced carbonate precipitation. It's based on the hydrolysis of urea or ureolysis. In MICP, the enzyme urease breaks urea down into carbonate ions and ammonia ions. So it creates carbonate ions in an aqueous solution. If there's calcium ion present, the calcium can combine with the carbonate and form calcium carbonate, which under the right environmental conditions will precipitate. There is we can't forget about the other half, though, of the ureolysis reaction, because not only does it create carbonate ions, but it creates ammonium ions, NH4 minus. And if we're using calcium chloride as the source of our carbonate, as the source of our calcium, then we have the chloride left over. The chloride will combine with the ammonium and produce a byproduct, ammonium chloride, that's a salt that's sometimes regulated as a groundwater contaminant. And so it's something we have to pay attention to when we're using MICP. I'll talk a little bit more about that in a bit. But MICP is by far the most popular biomediated process for geotechnical engineers. A quick Google Scholar search identified 716 new citations in January, February, and March of this year. Sometimes I think I get asked to review all of those for journals, the number of requests that I get. And since 2022, there have been 2,970 citations in Google Scholar on MICP for geotechnical purposes. It's a pretty impressive number. So MICP via uriolysis, we rely on the microbes, the M in the MICP, to provide the enzyme urease. And so ureolytic microbes, we can introduce those into the process in two different ways. We can use what we call bioaugmentation, where we can grow the microbes outside of the ground and then inject them into the ground along with the urea and the calcium chloride, or we can stimulate the ureolytic microbes in the ground. And so there's a theory in microbiology. You know, I became a geotechnical engineer because I didn't want to take chemistry and biology. And so I've been forced to learn more microbiology in the last 10 years than I ever thought I would know. But there's a philosophy in microbiology that every place you go, you have all the microbes you need for whatever microbial process you want to control. All you have to do is stimulate those microbes. So what we've learned from the early studies, that rather than augmentation, most of the time we're better off with biostimulation, where we start by stimulating the ureolytic microbes. How do we stimulate them? We provide them with the nutrients they want. If we feed them, they will grow. So biostimulation is a more, at least from my perspective, a preferable process. It's more cost effective, and you're using the natural microbes rather than introducing exotic microbes, which probably is beneficial in terms of the compatibility with the natural environment, but also with public acceptance. Because when you're putting microbes in the ground, people get upset. When you're just feeding the microbes that are already there, you're going to get a little bit easier public acceptance. The initial work on MICP was done by a group led by a fellow named Kucharski in Western Australia in the 1990s. He didn't call it MICP, he didn't call it uriolysis. He called it CIPS, the calcite in situ precipitation system, and he kept it as a trade secret. He didn't divulge what he was using. We know now that he was relying on uriolysis. Kucharski's work was picked up at University of Western Australia by Whiffen, and since that time, there have been a variety of investigators, Whiffen, Professor Chu, Leon van Passen at Delft, at ASU, and now at Boscalis, Carlos Santamarina, Jason DeYoung, Brina Montoya, Mike Gomez, Kenichi Soga, and others. It's not a comprehensive list, but there are a large number of investigators now looking at this process. What are the advantages and disadvantages of MICP? Well, one of the advantages, it's an extensively studied process. We can get consistent results in a wide variety of soils. And one of the things about MICP is once the microbes are there, we can probably reactivate them. They may go dormant, but if you need to reactivate the process, for instance, if an earthquake comes and breaks some of the bonds that you're relying on to mitigate liquefaction, hopefully by giving them a little bit more nutrients, we can reactivate that microbial community, and so create something of a self-healing process. That's yet to be proven, but that's kind of a goal. What are the disadvantages? Well, one of the disadvantages of MICP is multiple cycles of treatment are required for significant strength gain. Sometimes some of the papers I see that get megapascals in unconfined compressive strength are treating the soil 10, 12, 14, 20 times. Frankly, I don't know any ground improvement contractor who's going to want to use a process where he has to apply the treatment 20 times. Other issues other disadvantages of MICP is that the embodied energy may be similar to Portland cement. It's been being promoted in some places as a sustainable replacement for Portland cement, but urea comes from natural gas, and the embodied energy in urea is similar that we use in MICP is at the same level of the embodied energy in the Portland cement that we use for regular cementation. I'll talk about this again at the end when I talk about life cycle analysis. I mentioned the ammonium chloride byproduct that can be problematic, particularly for the multiple cycles of treatment, because you're going to be producing more ammonium with each treatment. Some applications require fewer treatments and mitigate this issue. Dust control, we don't need 8, 10, 12% carbonate. We just need maybe 1%. Liquefaction mitigation, it seems like we don't need as much carbonate as we do to get a high unconfined compression strength. There are also particle pore size limitations due to the size of the microbes. The microbes are actually kind of chunky. They have trouble fitting through the pore throats. So if you're generating the microbes outside of the soil and expecting them to penetrate into the soil, you can be limited to relatively clean, fine sands or coarser materials, but not finer materials. And if you have too many fines in the sand, over 10 to 15%, you might find some limitations based on pore size. What is the experience with MICP? Well, there's more and more all the time. Two of the seminal experiences. One is this large tank test done at Delft by Professor Van Tassen and some of his colleagues. 3 injection wells spaced 1.5 meters apart, 5 meters away, 3 extraction wells. This was in a big box. And as I remember, the sand in the box was up to the bottom of this yellow zone here. And their intent was to biocement the sand up to the yellow stripe at the bottom. And after the test was over, they broke down the box and they removed the loose soil. And this was the biocemented mass they were left with. Very high strength, durable mass. All in all, a very successful large scale test. More recently, UC Davis, the group led by Professor DeYoung, has been doing centrifuge experiments. So here's a centrifuge experiment by some of Dr. DeYoung's students and postdocs, where they've used MICP treatment to mitigate soil liquefaction. They've biocemented these blocks of soil, put little model foundations on top of them, spun it up to 50 or 60 Gs, and then shaken it with simulated earthquake shaking, and shown that the treatment is successful at mitigating the effects of liquefaction. The second process is EICP, and it's really the same chemical process as MICP. It uses ureolysis, hydrolysis of urea catalyzed by the enzyme urease. What's the difference? Well, the difference is the EICP uses free urease. It doesn't rely on microbial urease, although some people who do EICP cultivate the ureolytic microbes in the lab and then extract the urease from the microbes. In our lab, we extract it from plants, from a bean called the jack bean, a relative of the soybean that's particularly rich in urease. And so we have the free urease. We have found, somewhat accidentally, that adding powdered milk with the urease, originally proposed as a stabilizer for the enzyme, has had the unanticipated effect of providing very high strength at low carbonate content. So the plot over here is unconfined compression strength on the vertical axis, calcium carbonate on the horizontal axis. All these blue dots here are MICP testing with multiple cycles of treatment. More recently, the green triangles are some of the work done at UC Davis, where with fewer cycles of treatment, but still 6 to 8% carbonate, they've been able to get high strengths. The data you see here is 1 cycle of treatment with the EICP and 1 to 1.5% carbonate precipitated, generating strengths of almost 2 megapascals. Now, we're still trying to understand exactly why that happens, because so far, that's the only soil we've been able to get strengths that high with. But every time we put powdered milk additive with our enzyme solution, we get higher strengths than when we don't use the additive at lower carbonate contents. So this is a mechanism of great interest to us that's still under investigation by our students. Another thing we need to be careful of with the ICP, though, is that the reaction can help very quickly. The first time we tried to stabilize the soil with the ICP, we were really excited because we treated the soil column and there was carbonate everywhere. It was clogging the lines, it clogged the valves, it precipitated in the bottom of the reservoir. So we were sure we were biocementing the soil. And then we took the column apart and we found that precipitation was everywhere but in the soil column. Most of it was precipitating out of solution before it got into our column. And so we had to adjust our reaction rates. We had to adjust the speed at which we were introducing the substrates, mixing them together, and then introducing them to the specimen. And we find the same problem in the field. When we go out in the field and we treat soil, for instance, for dust control, where we spray on a carbonate solution, we have two separate components. We have one component that has the calcium chloride and the urea in solution, and we have another component that has the urease and powdered milk, and we only bring them together at the nozzle, because when we were bringing them together in the mixing tanks, by the time we got to the nozzle, we were losing a lot of precipitation. So the speed of reaction can be an issue with the ICP. So what are the advantages and disadvantages of EICP? Well, the advantages, we're going to use less substrate because we get higher strengths at lower carbonate contents, or the same strength at lower carbonate contents. That means lower cost, and maybe one and done. Maybe we can learn how to get that high strength in one cycle, and we don't have to treat the soil 10 times. When we use less substrate, we produce less ammonium chloride, so that's a little bit easier to manage. All of the carbon in the system goes to carbonate formation. In MICP, some of the carbon has to go to feeding the microbes. In EICP, all the carbon goes to forming carbonate. And then the enzyme is smaller than the microbes, so it can penetrate finer grained soils. It can penetrate into coarse silts. Disadvantage, we find this inconsistent biocementation. I'll show you an example of that in a minute. The mechanism is not well understood, so we need to understand that mechanism better. So here's some Ottawa sand. This is Ottawa 2030 sand. It's run, this is the sand that's retained on, passes the number 20 sieve and retained on the number 30 sieve. In the US, it's a standard testing sand, and it's found everywhere in the middle of the United States. It's a glacial outwash sand. It's 99.8% silicon dioxide, quartz. And you can buy it from a bunch of different quarries. And so we were buying it from one vendor, and this was the soil we treated with one cycle of treatment, and we got 1.8 megapascal in strength. We were running out of this sand, and we bought it from another quarry. It was a little cheaper, and we called this, and this is the second quarry we bought it from. Pretty much the same stuff, 99.8% carbon quartz, 2030 sand. But when we treated it, we got half the strength. We got 0.7 megapascal. Now we found that was pretty curious. So we bought Ottawa 2030 sand from a third quarry. We call this the B3 sand. In this sand, when we treated it, we got 0.2 megapascal. And I'll tell you, I didn't trust these results. We ran tests on all three of these sands 3 or 4 times to confirm these strengths. I just couldn't understand why we were getting, and I still don't understand, why we get 10 times higher strength with this Ottawa 2030 sand than with this Ottawa 2030 sand. So if we can understand what makes this sand so strong, and then we could learn how to treat other sands so that they perform the same way, then we would really have a process that we could use for foundation improvement, for making building materials, for a variety of important applications. And then I mentioned the reaction can be too fast, not only clogging in the nozzles and the tanks, but clogging in the soil around the injection points. If it precipitates too fast around the injection point, then the permeability will drop and it'll get harder and harder and eventually become impossible to introduce more substrate into the soil. What's our experience with EICP? Well, not as much lab data as MICP, but it's starting to accumulate. There are several investigators studying ways to control the reaction. You can reduce the pI of the solution. You can reduce the temperature. You can chill the EICP solution. There are some studies using fine-grained soils, silts and clays. Some of them purport to show improvement. I find the results inconclusive or unconvincing. One of the problems is that the EICP solution has salt in it, sodium chloride. So when you introduce sodium chloride into a saturated clay, you're going to suppress the double layer and you're going to change the strength anyway. And so the studies I've looked at that claim to improve the properties of clay through EICP treatment, it's not clear to me whether they're really improving the soil by precipitating carbonate or by suppressing the double layer with the salts that are being introduced to the soil. I need to be convinced of that. But moving on, we've done quite a bit of wind tunnel testing on this issue of fugitive dust control, and now we're in field trials. So we have large-scale field trials. We have one that's been completed and 3 that are pending within the next 6 months. So we're fortunate at Arizona State. We have a wind tunnel that was developed for the National Aeronautic and Space Administration to study windstorms on Mars. And we were able to use that. And so we would create a specimen of biocemented soil or treated soil that we would spray on a biocementation solution, place it in the bed of the wind tunnel, and then gradually increase the wind and measure what we call the detachment velocity of the sand. At what wind velocity do the sand particles start to detach? And we would compare that to bare soil and to wetted soil. So here's a plot of the threshold detachment velocity in meters per second, the velocity at which the sand starts to erode for 5 different conditions. The bare soil, a silty sand, where it started to erode at about 8 meters per second. Wetted soil. So one of the challenges with dust control is there's no regulatory standard. But the best available technologies consider keeping the soil wet. You go to a construction site, there's a guy with a hose who's spreading the soil, spreading water to keep the stockpiles wet. You go to a landfill, there's a water truck that's moving, or a construction site, land development site, you see the water truck keeping the soil wet. So we said, all right, let's also test the detachment velocity of wetted soil and consider that to be a regulatory standard. We wanted to do a control without enzyme, with just salt. And so this is what happened when we treated it with a 1 molar salt solution of sodium chloride. And then these are our 2 enzyme-induced carbonate precipitation tests, a 2 molar solution and a 1 molar solution. And both of them maxed out the wind tunnel. 25 meters per second was the maximum safe speed in the wind tunnel for the tests we were doing. And in both cases, we got to that maximum safe speed without wind erosion. So we consider that promising enough to begin to think about field trials. Whoops. And then I'll also talk about, that's dust control. We've also done field scale testing of making biocemented columns using EICP. In the same way you might make a soil cemented column or a stone column to support a foundation, we thought, well, why not make a biocemented column? So fugitive dust control. This is a worldwide air quality problem, due primarily to wind-blown soil. It's not industrial emissions. It's not vehicle emissions. Where I live in Arizona, in the USA, Maricopa County, the Phoenix area, we do not meet US air quality standards. And the reason we don't is because of wind-blown soil. It has nothing to do with vehicle emissions, or little to do with vehicle emissions. It's not just the US, the Southwest US, Eastern China, North Africa. Many areas around the world are plagued by blowing dust. I think most of us have been at construction sites have seen a picture like this with a piece of equipment moving across the site and leaving a cloud of dust behind it. In the States, the best available technologies are application of water and application of salt solutions. Salt solutions are a little bit more durable, but they're banned in many places because of the adverse impact on groundwater. Water works. But if you're in arid or semi-arid climate, which are the areas that are most susceptible to dust, those are areas where water is a valuable commodity. In fact, many of the headlines in the States these days are the fact that after 7 or 8 years of drought, the Western states are really reaching a critical point in terms of our water supply, and it may limit our growth. Again, Google Scholar, not quite as robust as MICP, but for EICP, there were 70 citations I found in 2021, 14 in the first 3 months of 2022. MICP for dust control, 106 citations in 2021 and 2021 and 2022. So biogeochemical fugitive dust control using either EICP or MICP, and in our test plots, we've done both. The concept is to create a wind erosion resistant carbonate crust by spraying on an EICP solution. The advantage compared to applying water is it's one and done. You don't have to continuously circulate to the site to keep the soil wet. The question is one and done for how long? Will it last a week? Will it last a month? Will it last a year? And that really affects the economics of the process. The disadvantages of this process are that it is a higher initial cost than water. You've got to buy the chemicals. If you're going to do MICP, you're going to use bio-augmentation, so you have to grow the microbial culture. EICP, you have to get the enzyme. In both cases, you need the urea and the calcium chloride. And so there's this potential environmental impact too, then from the ammonium, and then from the life cycle assessment from the urea. So, as I mentioned, we've moved from wind tunnel testing into the field. The one test session that we've completed was work that was done in collaboration with 3 industry partners, 2 landfill owners and a mining company. We sprayed on both EICP and MICP as a 2-component solution. So we had 2 tanks with our solutions and mixed them at the nozzle. We did an initial trial at an Arizona landfill in 2021 where we developed our deployment and monitoring techniques. Here are my students spraying the EICP. And then we did a second trial where we actually deployed 5 test strips, 1 for MICP, 1 for magnesium chloride salt, the mining industry standard, 1 for EICP, 1 untreated, and 1 where we mixed the EICP with a little bit of xanthan gum. So we supplemented the enzyme with some biopolymer. And so we are in the process of comparing the results. One of the things we learned from the first trial is we couldn't wait long enough for a windstorm to come and generate dust. In fact, before we had a significant windstorm, we had heavy rains, which washed away a lot of our crust. So in our second trial, we said, well, rather than waiting for wind, we'll create our own dust storm. So we dragged the chain link fence behind a pickup truck and drove back and forth on our test strips in order to generate fugitive dust and get some measurements to be able to compare these treatment techniques. So that field trial is completed. The PhD student who is writing that up will be defending her thesis next month. And we'll see what the comparison looks like of EICP to MICP to magnesium chloride. We have 3 more field tests in planning, looking at fallow agricultural field in Arizona, which is assumed to be a major source of fugitive dust. We have another mine tailing site we're going to treat for the Arizona Department of Environmental Quality. And then there's the Salton Sea. The Salton Sea is a man-made lake in Southern California that was formed when the canal that takes irrigation water from the Colorado River and Hoover Dam to Southern California breached, and it filled in a low-lying depression. Over the years, that depression was sustained by agricultural runoff. But now, after 7 years of drought, the Salton Sea is shrinking. And when it shrinks, it exposes these playas, these mud flats, that are contaminated with agricultural runoff, herbicides and pesticides. And when the mud flats dry out and the wind blows, it creates toxic dust that blows into the neighboring communities. So this fall, we will be deploying an EICP and an MICP test section adjacent to the Salton Sea. And there are several other sites that have contacted us. The Highway Department in the Northeast US that say after the spring thaw, they have fugitive dust problems. An iron ore mine in Minnesota that said the same thing. When the ground thaws and dries out, they have fugitive dust. And so we're looking at the field, at the freeze-thaw resistance of our carbonate spray to see if it has applications in those kinds of climates. One other application to talk about on EICP, and that is making biocemented soil nails and columns. So the concept is to create columns, either vertical or angled, of biocemented sand for ground improvement. And we take inspiration from other improvement processes. I like to show this picture over here on the left. This is from Lizzie, as quoted by Mitchell and Villet. And Lizzie, this was really soil nailing, but I show this because he called these root piles. he was one of the first with a bio-inspired design. He developed this idea of reinforcing the soil, the slope, the same way that roots reinforce the ground. So he was really the first bio-inspired engineer. But if we look at what we use columns for in geotechnical practice, we look at using them for soil nails. We can support foundations. We can create soil mixed columns for liquefaction mitigation and ground improvement, support embankments and retaining walls. Lots of applications for biocement or for improved soil improvement via columnar enforcement. So one of the first things we did was biocemented soil nails. And so we had this wooden box that it's a little odd shaped. It's 0.15 meters wide. And that's basically because it's the width of a sheet of paper. And we would use this box to demonstrate for our students how we could use paper to build a reinforced earth wall. We would lay the sand in layers and fold it over at the front and build up a wall, and then allow the students to stand on it. We said, well, maybe we can also do that with soil nails. So we introduced 4 tubes, perforated tubes at 15 degrees through the face. We drilled holes in the faceboard. We inserted these tubes, and then we injected 155 milliliters of EICP solution into each tube, let it cure, and then I only show this in presentations. If someone asked me for my slide, I remove it because this is one of my graduate students standing on the biocemented wall and violating about 3 health and safety protocols in our laboratory. But I think it gets a point across. And yeah, he weighed about 75 kilograms. And this is after the fact. After we excavated around our soil nails, this is what our biocemented column looked like. Moving on, we decided to create some field scale columns. Moving on, we created some mid-scale columns in wooden boxes 1 meter high. And there's a paper in Soils and Foundations that discusses of mid-scale boxes. But we used that as a prelude to creating these field scale columns in our test pit. So CBBG, the Center for Bio-Mediated Geotechnics, has a test pit on one of the ASU campuses. We're about 6 meters by 2.5 meters in the main bay, and then we have an adjacent bay here that's 3 meters by 1.8 meters. It's 3.8 meters deep. We can fill it up with quarry sand. We have a crane. We can put reaction beams across the pit at 3 locations. And so we took advantage of this to create some EICP columns, enzyme-induced carbon and precipitation columns. And we did it using conventional grouting equipment. We did it using a tube and manchette grouting approach, a perforated tube that we would pack off in sections and insert our cementation solution. Now, in a conventional tube and manchette, you drill down, you create a borehole, you fill it with a weak bentonite cement, you install your manchette, your tube and manchette, and then you inject your cementation solution from the bottom up. We short-circuited the process. We hung our tube and manchettes from wooden grill work over the pit, and we filled the sand around the tube and manchettes, simply because that was easier and cheaper for us. But we created 7 columns. Actually, we created 8, but the 8th got destroyed in the construction process. We treated each column to 3 cycles of EICP at 24 hours interval. Why 3 cycles? Well, we had a target strength of 500 kPa. The grouting literature says that the minimum strength for permeation grouting of soils, effective permeation grouting, was 500 kPa. So we did laboratory testing, and we found out we needed 3 cycles of EICP to get the 500 kPa. So that's what we used in the field. We injected them at 24-hour intervals, and we used a crude urease enzyme that we produced on site, and I'll talk more about that in a minute. So this is our test pit layout. This shows 8 columns, but this one here with an X got run over by the CPT truck when we were first doing our exploration, our pre-grouting exploration. And it's kind of sad that it did, because this was the one that had a metal pipe that would have allowed us to do a pull-up test. Our other columns have a plastic pipe for the tube and manchette. And so if we did a pull-out test, we would yield the pipe before we pulled the column out of the soil. So we had one metal pipe, but got run over by the CPT truck. I guess that's research for you. So we had these 7 columns. They varied in diameter from 0.3 of a meter to a meter. They varied in height. The 1 meter column, just for economy, we only made it 1 meter high, starting at the bottom. If we tried to create a 1 meter column up by the surface, we were afraid we would just get fracturing. We varied the injection rate. When we make our crude enzyme, in the beginning, we would peel the husks off the jack bean, which is a very laborious process. We said, let's see what happens if we don't take the husks off. So we made some columns with no husks, with the husks left on, with the husks left off. We instrumented 2 columns with moisture sensors. We pushed the CPT through 2 columns. We did seismic testing on 2 columns, and we did a pile load test on 1 column. So this illustrates the tuba machette. It was hooked up to a peristaltic pump. It fed the solution in. We would start at the bottom, and these are 6 centimeter intervals that we would pack off. And then these were ports with a rubber sleeve around them. When we injected the ICP solution under pressure, the sleeve separated from the tube and allowed the cementation solution to flow in. And each time we injected 1 pore volume for the diameter of the column we were shooting for. Now, between each injection port, we had a geosynthetic collar. Because we weren't putting this in a bentonite borehole, we were worried about vertical migration of the solution up and down the tuba manchette. So as we placed the soil from the bottom of the pit up, when we got to the level of 1 collar, we put a small geosynthetic apron on it, and then we continued placing the soil to prevent migration of the injection solution up along the column. This shows our pump setup, peristaltic pump that was feeding the solution into the tuba machette. These are the results. So at the right, we're excavating down, taking samples from the columns. You can see sometimes we had very good control, making a circular column of the target diameter. Our target diameters were all within about 7%. Our actual diameters were all within 7% of the target diameter that we were shooting for. And you can see my students here excavating the pit. Much better health and safety precautions this time, although short sleeve shirts is not a good idea. But this was one of the columns after we'd almost excavated it down to the bottom. And this is one of my graduate students. She's tall. She's 2 meters tall. So this was a 2.4 meter tall column. And you can, after we excavated it and we brushed off all the loose soil, this is what was left. And we consider that a success. The paper describing these biocemented columns is under review for publication in the ASC Journal of Geotechnical and Geoenvironmental Engineering. I mentioned that we made the enzyme on site. Typically, when we first started doing this, we would buy enzyme from the pharmaceutical companies, and it was very expensive. A little bottle would be $700. And I kept telling my students, don't worry about the cost of the enzyme. This is lab grade, food grade enzyme. We don't need enzyme this pure, but this is our best source right now. So at one point we started making our own enzyme, and we started making it the same way the pharmaceutical companies do it. So the lab grade enzyme extraction process, we would dehusk the beans, we would soak them in a buffer solution, we would put them in a blender and grind them up, filter them, put them in a centrifuge, take this supernatant from the centrifuge, run it through another filter, and then purify the enzyme through 2 steps of acetone fractionation. So soaking in a buffer, grinding, filtering. This first filtration step was with cheesecloths to remove the solids, centrifuging to remove more solids, filtering it through steel wool to remove the fats. That gave us a crude extract that went through acetone fractionation, centrifugation, acetone fractionation, more centrifugation, and finally the lab grade purified enzyme. We simplified the extraction process. We replaced the buffer with water. We eliminated the ultracentrifugation and we eliminated dehusking. So we took the beans and we soaked the whole jack beans in water. Then we put them in the blender. We ran it through the cheesecloth to remove the solids. We centrifuged it once. Well, we filtered it. We skipped the first centrifugation. we went right to the second filtration step and ran it through the steel wool to remove the fats. And then we took that crude enzyme and we used that to treat the soil. We skipped all of these other steps in the process. What's the result? Well, what we found out was not only is it cheaper, but it was more effective than the pharmaceutical grade enzyme. It provided higher strength at the same content as the refined enzyme. So here's a plot showing unconfined compression strength. The solid bars are the unconfined compression strength, and the carbonate content for the sigma Aldrich low activity pharmaceutical enzyme, the sigma Aldrich high activity pharmaceutical enzyme, Fisher Scientific enzyme, which is a less purified enzyme than sigma Aldrich, the crude extract when we used water, and the crude extract when we used the buffer. And you can see they all produce pretty much the same carbonate content. The two crude extracts are a little bit less, but not much. I mean, the difference between 1.6% and 1.8% carbonate by weight. The high activity enzyme, the expensive pharma grade enzyme, had the worst performance. It had the lowest unconfined compression strength, 200 kPa. The low activity, a little bit better, 300 kPa. The Fisher Scientific, the best at 1,000 kPa, and the two crude extracts, 700 kPa. So we got higher strength at the same carbonate content as the refined enzyme. The role, and my colleagues who are biogeochemists, I'm always hesitant to say this because somebody might think I understand this, but I'm told it's because of the role of the complementary proteins that are in the crude extract or in the Fisher extract. Well, when you do cost analysis, you find the use of the crude extract, it reduces the cost of treatment significantly. It reduces the material cost per cycle of treatment by 75%. So here's our cost analysis using the commercial enzyme, where it was about $60 per liter of VICP solution, 60 US dollars. The crude extract and the simplified crude extract reduced that to about $15. So a 25% reduction or a 75% reduction in the cost of treatment using the crude enzyme. All right, well, one more process to talk about, MIDP or MID. MITV, microbially induced desaturation and precipitation. These days, we don't worry too much about the precipitation. We just call it microbially induced desaturation. It's an alternative carbonate precipitation process. It also desaturates the soil because while precipitating carbonate, it also generates nitrogen gas. And the nitrogen gas is relatively insoluble. It forms bubbles in the pores, and it desaturates the soil. The process is sometimes called denitrification. You need to introduce nitrate to the soil. The nitrate is reduced to nitrite and then to nitrogen and carbon dioxide. The carbon dioxide goes into solution and provides us the carbonate we need for calcium carbonate precipitation. If we want to precipitate carbonate, the nitrogen is insoluble. It stays as a bubble in solution and desaturates the soil. The good things about this are, according to my microbiologist colleagues, is that the denitrifying bacteria are ubiquitous. They're everywhere. You just need to stimulate them. The carbon dioxide goes into solution, creates those carbonate ions, and the relatively insoluble nitrogen gas desaturates the soil. The downside, if you want to precipitate carbonate, is that the carbonate precipitation is very slow. It can take a year to precipitate 1% carbonate. But the desaturation is almost immediate. In a day or two, you desaturate the soil. So here's some test results. This is back when we looked at liquefaction mitigation via microbial denitrification as a two-stage process. Stage one, desaturation. Over here on the right, these are cyclic strength curves. This is the cyclic stress ratio. Somehow I lost the legend. Versus the number of cycles of liquefaction. The difference between 100% saturation and even just 3% saturation. We can consistently get below 90% desaturation with MID. But with even 3% desaturation, you get a 20 to 40% increase in the cyclic strength of the soil. Even 1% desaturation. That's why when we do our cyclic triaxial test, we go to such great lengths to saturate the soil with back pressure saturation to get a B value of 0.98. It's a laborious process because even a little bit of desaturation significantly reduces the strength of the soil. Over here, what we found encouragingly is that the carbonate precipitation was also very efficient, that very small amounts of carbonate significantly increased the liquefaction resistance. So with just 0.4% calcium carbonate by weight, we get like a 20% increase in carbonate content. With 0.9 or 1% calcium carbonate, about a 40% or 50% increase in the cyclic shear strength. This scale starts at 0.15, so these distances are a little deceiving. And this is what some of the biocemented sand look like. What are the advantages and disadvantages of MIDP? Well, my environmental engineering colleagues tell me that the denitrification process is extensively studied and well understood. It's used in waste and water treatment plants. The desaturation mitigates liquefaction. There are benign byproducts unless sulfate is present. If you have sulfate present, you could be generating hydrogen sulfide, which is toxic gas. But the precipitation is very efficient. So this is one of my favorite pictures taken by my student, Sean O'Donnell. And these are two Ottawa sand particles, two Ottawa 2030 sand particles on the right and left. This circular surface, this is a scanning electron microscope image. This is the remnant of a bubble. That's why it's such a perfect circle. This is organic matter that gathered around the bubble to outline it for us. Very nice of the organic matter to do that for us. But notice how the bubble has pushed the calcium carbonate crystals, that's what these are. You can tell by their morphology that they're calcium carbonate, calcite, into the contact zone between the soil particles. That's exactly where we want it. That's where we want it to increase the strength. When we do MICP, sometimes the calcium carbonate coats the soil particles and then slowly grows to create contacts between the particles. In MIDP, the bubbles push those calcite particles into the contact zone, which is exactly where we want them. So at the same carbonate content, we get higher strengths with MIDP. And at low carbonate contents, we get high strengths. Of course, the milk does the same thing with the EICP. It focuses the precipitation, not quite as efficiently as a bubble, but it seems like it's focusing the precipitation at the contacts. What are the disadvantages? Precipitation is slow. So if you're relying on precipitation, you're going to have to treat for a long time. But, you know, if you want to mitigate liquefaction and it takes 6 months to a year and you're designing for an earthquake that happens once every 2,500 years, maybe that's acceptable. The issue with desaturation is the longevity. How long will the soil remain desaturated? There's good evidence that in sands, it could last for decades, but I think we still need a little bit more evidence. We're doing some monitoring right now of a site where we've desaturated a low plasticity silt. But we find from tank tests in the lab that the gas, if you produce too much gas, they'll coalesce on a lens and they'll vent. Although even when it vents, the residual degree of saturation is still on the order of 90%. There is a potential for hydrogen sulfide, H2S, if sulfate is present in the soil. And the N2 gas can lead to bioclogging. Remember, desaturation reduces the permeability. So as you create more and more bubbles, it gets harder and harder to introduce the substrate into the soil. We have done centrifuge testing of liquefaction, pardon my spelling, centrifuge testing of liquefaction mitigation via MID. And this was a collaboration between ASU and UC Davis. We used the 1 meter centrifuge at UC Davis, spun our models up to about 80 G. This is the model, 14 centimeters high, and we're about 50 centimeters wide. Pore pressure transducers in the middle, and bender elements so we can measure shear wave velocity in flight. This is the degree of saturation as measured by these GS3 sensors versus time. The shaded zones, we spun this up and we shook it twice. Because we couldn't leave the centrifuge spinning overnight, we spun it up, we shook it once, we spun it down, came back the next day, spun it back up again, and shook it again with higher accelerations because we weren't able to liquefy it on the first day. And you can see we got the degree of saturation down below 85%. Then when we shook it, we lost some saturation. In the upper layers, it rose back up to about 90%, although then it settled back down again. We let it sit for a day, and then we had a similar but even better result the next day in terms of residual saturation. These are the results. Shake number, the amplitude at the base of our model and the number of cycles we shook it with. We used uniform loading, and we had a model with unimproved soil, and it liquefied at between 0.05 and 0.10 G. So it should have liquefied by the fourth shake here, or by the fifth shake at 0.10 G. And yet we got up to 0.36 G, and at 0.36 G, we had a pore pressure ratio of 0.7. We still didn't liquefy the soil. Then we shut it down overnight. We went back, and the first time we shook it the next day at 0.4 G again, we did get liquefaction of the surface layer. And we think that's because when we spun the model down, some of the soil vented and it loosened the soil layer. Because after that, we continued to increase the acceleration, and the pore pressure ratio still stayed very low. So we took this as a good indication that desaturation is an effective way to mitigate liquefaction. We have moved into the field with microbially induced desaturation. We did this project in collaboration with Portland State University, the University of Texas, Kent Stokey, Oregon Division of Oil and Gas and Minerals Industry was one of our partners. We were funded by the National Science Foundation from their Natural Hazard Engineering Research Infrastructure Project, and of course CBBG. And we successfully desaturated 2 sites in the Port of Portland. So Portland, Oregon is a port at the confluence of 2 rivers, the Columbia River and the Willamette River. And both rivers are lined with liquefiable soil deposits, although they tend to be low plasticity silts that in a moderate earthquake are not predicted to liquefy, but Portland is subject to magnitude 9 subduction zone earthquakes in the subduction zone off the west coast of the US. And so the analysis suggested that these silty sands, low plasticity sandy silts, would liquefy in the subduction zone earthquake, and 90% of the energy resources for the state of Oregon come in through the port, and they're concentrated in this critical energy infrastructure hub where there's all these relatively old steel tanks built on liquefiable, potentially liquefiable soil. And then the airport is also on liquefiable silt. So we did 2 test sections, one in the critical energy hub and one at the airport. The critical energy hub, they did some construction there, so we lost that test section, but the one at the airport, we're still monitoring. It's been 3 years now. So these are the results. This is the soil profile. We have this low plasticity silt that extended from 1.5 to 6 meters below the ground surface. We had a central extraction well surrounded by 4 injection wells, and we treated a radius of about 6 meters or 8 meters. We monitored desaturation by monitoring the pressure wave, the P wave velocity. And so this was the P wave velocity before treatment. 1,500 meters per second is an indication of saturated soil. Up here in the upper zone where we had lower values, that's because we're in the zone of water table fluctuation. So the soil is not saturated in that zone. So it might not be liquefiable, but certainly down here, we have to worry about liquefaction. And you can see our treatment successfully lowered the shear wave velocity from saturated state, 1,500 meters per second, to 1,000 meters per second. Now, we wanted to shake the site with the big shakers that Professor Stokey has, but unfortunately, we couldn't generate a strong enough motion at this depth to generate significant pore pressures. But we've been continuing to monitor the site. We still see this level of P wave velocity in the treatment zone, and we're working on plans to go back with different equipment and subject to accelerations significant enough to start generating pore pressures. We've done some financial analysis of MID. We call it a techno-economic analysis. And we did this in collaboration with a local ground improvement contractor to make sure we got the costing right. We let them do all the costing. We let them design the alternative. We compared MID, microbial induced desaturation, to permeation grouting. And so we had a substation with a 12 meter by 24 meter footprint, water table at a depth of 1.5 meters, 7.6 meters of clean sand, 6 meters that were below the water table, uniform clean sand, relative density about 70%. and we compared permeation grouting to desaturation. It was developed in collaboration with Condon Johnson, West Coast ground improvement contractor. We designed the MID system. We had wells at 3-meter spacing, injection wells on one side of the building, extraction wells on the other side of the building, 12 meters away. And so we would pump our substrate into the injection wells and draw it across to the extraction wells to desaturate the soil. The permeation grouting system designed by the grouting contractor had grouting pipes at 1.5 meters center, but at different angles. So the idea was to create a grouted mass beneath the buildings that would resist liquefaction. Each injection point actually had 3 pipes at different inclinations. So this is the cost analysis. I won't go into the details. I'll go to the bottom line. The permeation grouting solution cost $600,000, and the desaturation solution was about 30% of that, $180,000. So significantly cheaper. And we picked a situation that was amenable to permeation grouting. So it was a medium clean sand. If we had a silty sand or we had a finer grain sand, we wouldn't have been able to use permeation grouting. We would have had to use compaction grouting, which would have increased the cost significantly. Just a few words about precipitation of other minerals and metalloids. So one mineral that's of interest to us is phosphorus, because farmland in the US, runoff from farmland can be impacted by phosphorus. So we worked with an industrial partner who had a steel manufacturer who had all this slag on site that they were looking for beneficial use for. And we knew from some previous work had been done that running calcium-rich, phosphorus-rich water through the slag would precipitate the phosphorus. And so the idea was we went up to a farm in Wisconsin. We put in a filter bed that was filled with this slag, and then downstream of the filter bed, we had the settling basin. So the idea was we would run the agricultural runoff that we collected from one of the tile drains under this field through the filter into the settling basin. The phosphorus would settle out. Then we would discharge the water into a treatment wetlands that would remove the nitrogen. And in that way, we would clean the agricultural runoff. The problem we had is that all the phosphorus precipitated, it precipitated instantly, and it just clogged all the slag. It never made it to the settling basin. And so after 1 year of operation, we had to replace all of the slag. And so we're still thinking about ways where we could slow down the precipitation and make this a more viable process. Other minerals, we have one of our investigators is looking at precipitating iron to create subsurface barriers. You know, in some situations, you might be able to precipitate salt for temporary stabilization. Precipitation of contaminants is of great interest to our environmental engineers. There's been work done on co-precipitating strontium to calcium carbonate, work done by the Idaho National Engineering Labs at the Hanford site in the US, where the groundwater is contaminated by strontium from production of nuclear weapons, and it's moving towards the Columbia River. And MICP, or I guess the ICP, can be used to co-precipitate strontium as strontium carbonate and sequester it in the soil. One of our colleagues in New Mexico State is looking at precipitating selenium and arsenic biogeotechnically, excuse me, yes, selenium and arsenic as selenate and arsenate, and then chromium is another contaminant that we think we might be able to treat, precipitate, or at least treat biologically. What are the challenges with these mineral precipitation processes? Fines content. When we go to one of the issues with biocementing a fine-grained sand or a fine-grained soil is that the number of interparticle contacts increases with the square of the particle size. So if you half the particle size, you have 4 times as many contacts to cement. And unless you can cement most of the contacts, you're not going to get a significant increase in strain. So it makes it a real challenge for improving fine-grained soils. Permeability, we've talked about that. It clogs up the soil. It makes it difficult to deliver the substrates. So we get this bioclogging due to mineral precipitation, growth of organic matter and gas generation, saturation of the media, the permanence and reversibility still needs to be studied, and managing the byproducts. processes. I thought it's worth mentioning transformation of organic chemicals. It's perhaps the most biogeochemical process thanks to our environmental engineers. And so processes of interest include anaerobic and aerobic degradation. Some of you know I used to do a lot of landfill work where we take advantage of both anaerobic and aerobic degradation to degrade solid waste, create more capacity in our landfills. Reductive dechlorination, treating chlorinated solvents by reducing them to ethene microbiologically is an important application. Denitrification and ureolysis are both basically taking chemicals and transforming to urea. Sometimes one of my pet peeves is that people automatically assume because we're using a bio-mediated process, it's going to be sustainability. Just because a process is bio-mediated doesn't mean it's sustainable or environmentally friendly. That has to be proven. The embodied energy in EICP or MICP compared to Portland cement, it's about a wash. Urea takes 22 megajoules per kilogram to generate urea. It takes 4.5 megajoules per kilogram for Portland cement. When you look at the quantities that we need for MICP or EICP versus Portland cement, it's pretty much a wash in terms of embodied energy, and it's pretty much a wash in terms of embodied carbon. So you can't automatically assume that MICP and EICP are going to be environmentally more sustainable. And the embodied energy is just one aspect of the sustainability. So when we do a sustainability assessment, you know, we need to consider the three-legged stool. We need to consider the cost and the permanence. We need to consider the energy consumption and the environmental impacts. We need to evaluate all biogeotechnologies to demonstrate the sustainability using a life cycle sustainability assessment, where we consider the three components of LCSA: the life cycle cost assessment, the life cycle environmental assessment, life cycle costs, life cycle environmental assessment, and then the social impacts of what we're doing. And so that's something that we try and do at CBBG. The lead there are our colleagues at UC Davis, but all of the partners have bought into the LCSA process. We've done a preliminary LCSA assessment of EICP for fugitive dust. Alyssa Kendall and her student, Alana Raymond, along with other members of the CBBG team, looking at when does the higher initial cost of EICP offset using water. And what we found is if the EICP lasts more than 2 weeks, it'll use less water, consume less fuel, and generate less emission than running a water truck twice a day. We do have to, though, consider environmental impacts. We've talked about the ammonium chloride byproduct leading to acidification, eutrophication, but it's not a foregone conclusion that the ammonium chloride is going to get into the groundwater. We need to do some kind of fate and transport analysis to see where it's going to go. And for dust control, ammonium chloride is a fertilizer. It might be able to stimulate vegetation, and that'll certainly mitigate the environmental impact. So this is a snapshot of the results from our LCSA for 2 weeks of durability, comparing primary energy consumption, global warming potential, project cost, social costs based on greenhouse gas emissions, the acidification potential. That's the one place where the EICP loses. And then water consumption, where it comes out way ahead. And of course, it's hard to combine these metrics. It's up to the decision maker to apply his own value judgments when you have metrics that show different benefits. Different processes are more beneficial and less beneficial. But in this case, to me, it's pretty clear that if we can show the EICP can last for 2 weeks, it's a superior process to using water for dust control. Finally, I thought I should say a few words about CBBG, the Center for Bio-Mediated and Bio-Inspired Geotechnics. We've been funded by the U.S. National Science Foundation. We're in our 8th year of a 10-year funding period, a total funding from NSF of $36 million Then our universities were each required to put up 20% of additional funding. So that added another 7.2 million. We've added supplements to that. We've added industry funding to that. And so we're well over $50 million in investment by the time we're done 2 years from now. And we don't just do research. We do education, outreach, workforce development. It's four universities that span the U.S. from coast to coast, from California to Georgia, and include ASU and New Mexico State. We have education and outreach programs. We have a research experience for undergraduate programs where we bring undergraduate students in from other institutions, not from our institutions, who spend 12 to 14 weeks working in our labs in the summer. We bring teachers in. We bring elementary school, high school, and junior college teachers into our labs for a 5-week program where they develop classes, lessons that they take back to their classes and that we publish online. And so there's a library of lessons for everything from grade 4 to junior college on biogeochemics that have been published online that are available. Probably the best place to find it is at the ASCE, American Society for Engineering Education website. And we go into the K-12 classrooms and we do public outreach at events at our universities. And then we have this industry partner program where our industry partners cover the full range of interested parties, consultants, contractors, owners, and agencies. And I have to give this disclaimer. Much of the work described herein was supported under NSF Cooperative Agreement 1449501, but the opinions, findings, conclusions, and recommendations expressed herein are those of me and do not necessarily reflect those of the National Science Foundation. Just a quick snapshot of our industry partners: large international mining company, local landfill, a charitable foundation that works in Arizona, the U.S. Environmental Protection Agency, GeoPeer, City of Phoenix, Arizona Department of Environmental Quality, geotechnical consultants, Haley & Aldrich, Geologic, and Geosyntec, groundwater technology from the Netherlands, Department of Transportation from Arizona, Keller, North America, Nicholson, and Menard. And they have provided both technical support for us and services in kind and cash. And so we're grateful for their support. Finally, I'd like to invite everybody to to our international conference on bio-mediated and bio-inspired geotechnics in 2025. It'll be at ASU in Tempe, May 19th to 21. A call for papers will be coming out in the next 1 or 2 weeks. And I invite you all to join us there. There'll be more information in the call for papers. So the biogeotechnical future. I think we've just scratched the surface. Only a few processes and methods have been explored to date. There are opportunities to do much more, and I think you just need to use your imagination to think of places where biogeotechnics can play a role. And so with that, I'll conclude my presentation. I hope I didn't go too long, and I thank you all for listening. And I don't know if we have time, but I would be happy to answer questions.
Thank you so much, Professor Kavazanjian, for a very enlightening and also most comprehensive lecture on the biogeotechnics. In addition to what Professor Kavazanjian has said, due to the overwhelming enthusiastics in this research, we have also started a new international journal on biogeotechnics. Professor Kavazanjian is the honorable editor-in-chief for this journal. It is an open access journal, so in other words, you will be able to access all the papers published from this journal free of charge. In fact, for the time being, you can also submit papers to this journal, which is also free of charge. As you can see from here, so I'm also one of the editors for this journal. Now we open the floor for questions. Maybe before I start to invite the audience for questions, let me just ask one question for Professor Kavazanjian. You have give a very elegant summary on the recent progress for biocement and its application. So you mentioned the MSCP, EICP. I just wondering, in your opinion, which method do you think will be most promising?
Oh, you're going to get me in trouble. You're going to get me in trouble with my colleagues. I think they all have a role. I think they all have a place. You know, if it didn't come across, I'm a big fan of EICP for biocementation. I'm a big fan of EICP because it offers the promise of fewer treatment and less byproduct. And if we can figure out why we get that high strength in that one sand and how to treat other sands through that process to get those kind of, even half that strength, even 1 megapascal, you know, the applications are boundless. I also think MID has great potential for mitigating liquefaction under existing facilities. You know, when there's nothing on the site, mitigating liquefaction is easy. We get a crane and a big weight and we lift it up and drop it. But when there are facilities there, underground infrastructure or buildings, there's really no cost-effective solution right now. So I think MID offers a cost-effective solution for mitigating the trillions, literally trillions of dollars at risk worldwide to liquefaction. You know, 2011 Christchurch earthquake, magnitude 6.3, caused over $20 billion in liquefaction. One small earthquake in New Zealand. So you look at the threat worldwide. So I like EICP for biocementation. I like MID for liquefaction mitigation.
Yeah, I agree with you fully. The biodesaturation is a very promising method, as you have demonstrated. So it is also very much more cost effective. I just like to add on what you have said. I see another reason is for liquefaction. We have to treat the soil for a large extent. I mean, as demonstrated by the recent earthquake in Indonesia. So the land is moving. You can see the buildings are moving with the ground. So in other words, you can not just treat the foundations, you have to treat the surroundings. So the scale is much, much bigger. So the unit cost for the treatment will be a major consideration. So certainly your method EID and will be the biodesaturation will be, in my opinion, one of the most promising methods for liquefaction mitigation.
I think we're in agreement on
that. Before I read the questions in the chat box, I'd just like to ask the audience, are there any questions you can ask directly to Professor Kavazanjian? You can just unmute yourself and then you can ask us questions. While we're waiting for the questions, let me just read one question in the chat box. You can also read it from the chat box. It says, "Thank you, Professor Kavazanjian, for your very enlightening lecture. I understand the UCS strengths of those cemented materials vary considerably with a large coefficient of variation even under well-controlled lab conditions. Given the fact that the nature ground is heterogeneous with spatially varying soil properties, and the safety and the serviceability of many geotechnical problems very much dependent on the weakest steep plane. So in this sense, the performance of MICP/EICP treated the ground somehow depends on spatial homogeneity. So do you have any suggestions regarding how to ensure spatial uniformity of the bio-treated ground in real field application? I think this is a very good question.
That's a very good question. It's a very good question. So that's why we do the biocemented columns. You know, in the biocemented columns, we have more control. And you know, there's also the option of doing a soil mixed column with an auger. We've done that on a lab scale. But with the biocemented columns, we feel, you know, well, if you have a weak clay lens, there's not much we can do about it. So, you know, the MICP might not be applicable to those situations. But as long as we have a granular soil, even if it varies between a clean sand and a silty sand, we think that the biocemented columns are a viable approach for supporting foundations. You know, mitigating landslides and slope stability, yeah, that's a challenging problem that may not be amenable to MICP and EICP. But the desaturation, what we find for liquefaction mitigation is it actually works in our favor. The zones where you get preferential flow, the coarser sand zones are where you need the treatment. And if you have out of fines, the soil's not going to be liquefiable. So we think that for MID, the heterogeneity, and Professor Van Passen has done some tank tests in the stratified silt and sand system. And it seems to support our contention that the substrate will flow through the higher permeability layers, which are the ones we need to treat for liquefaction.
Yes, thank you. If I may add on, even for cement-treated soil, we have the same problem. We have, spatial variability. But on the other hand, if we are dealing with a larger scale in statistics, this is also called the spatial average. So the standard deviation will reduce over a larger scale. So for example, if you're dealing with a column, if the column is more than 10 meters, and then also within the 10 meters, there are variation in the properties in the treatment. But however, the average over the 10 meters and the standard deviation can be small. So I'm sure that the person who asked the question is actually our young faculty who just joined us, joined the NTU not long ago, to Dr. Shi. He's expert on machine learning as well as soil variability. So you will understand the spatial average meaning.
Well, and I'll add that, you know, Professor Boulanger at Davis has done kind of a random field finite element analysis where he randomly varies the properties and has shown how that kind of averaging works and can work to your advantage.
Now let's move on to the second question. I have a general question and a technical question. So some of the bio-cementing processes are not found in soils. Will you think those processes are worth to have a try? So how could we evaluate the eco problems by using them? By using EICP, do you suggest us always using milk as one of the recipes?
We find that the milk, one, it's a stabilizer for the enzyme, which is why we first started using it. But I don't, you know, if you're looking for strength gain, we just find whenever we use the milk, we get more strength. So there's no reason, we always use it now. So I'm hard pressed to think of a situation where we wouldn't want to, a reason why we wouldn't want to use the milk. It's not much. It's non-fat powdered dry milk, and it's very little. It's like 0.4 grams per liter.
Right. Now let's move on to the next question.
So I can, there's a question here: during treatment of the soil below the substrate station, does the existing substrate station settle? No, not during treatment. The question is, when the earthquake comes, even if the soil doesn't liquefy, will there still be some settlement?
Mm-hmm.
And there may be a little bit.
Right. Ed, can you also answer the next question? So those questions are from our practicing engineers in Singapore.
Sure. So the next question is MICP EICP is a potential solution for seismic areas and or for the creation of caverns. Yes, I think one of the applications is for tunneling, for stabilizing sands for tunneling. And you know what the tunnel is called, both running and flowing, running sand being a dry sand, flowing sand being a saturated sand. That's an application we've always been interested in, going in, biocementing the soil, and then tunneling through the biocementation zone. I think that's a very workable solution. Now, a cavern, a wide span cavern, that's a different issue. Then, you know, you need some tensile strength and you need some very high unconfined strength. But for tunneling, you know, micro tunneling or even a small utility tunnel, I think that MICP, ICP is very viable.
Yes, you may, if I may add on, the EICP or MICP will have a role to play in terms of seepage control, particularly for rock joints. For very fine joints, the cement grout may not be able to be applied. In this case, I think biogas would be a good option in the sense bacterial cells are very, very small and enzymes are even smaller. So they will be able to penetrate very fine rock cracks. So in fact, we have done a research project on grouting of rock fissures using biocement solutions.
And there are people looking at sealing concrete cracks with MICP, ICP.
Yes, that's right. Another application would be self-healing concrete. Yeah. It's using the same process. There's another question which we have not answered is still on the consistency and the uniformity.
Yeah, you know, it depends on the application. You know, I mean, for dust control, where we're spraying it on the surface, I think it's very consistent and very uniform. You know, if the superficial soil changes, the crust will change, but it's a very consistent process. When we made those columns in our test pit, we got very consistent results, but admittedly that was a man-made soil deposit that was uniform. So it's an issue, you know, like it's an issue with any new technology. And in a uniform soil, I think the process will be uniform. And if we have a non-uniform soil, then it's an issue that may have to be dealt with like geostatistics, as you mentioned.
Why it has been 1 hour 40 minutes. At the peak, we have more than 150 participants. So currently, we still have 143 participants. So this is one of the most well-attended seminars organized by us. Let's show our appreciation to Professor Kavazanjian again. Thank you very much, Ed, for a very enlightening and very comprehensive lecture. We have benefited greatly from your lecture. Yeah, thank you very much.
Thank you. It was my pleasure. It was my honor. I appreciate the opportunity. Thank you all.
Yeah. Thank you so much. Yeah, if you still have questions, you can email to me, and then I can pass on the questions to Professor Kavazanjian. Thank you very much for your participation. Before you go, let me just make an announcement. So by next month, we will have another seminar offered by, again, another two most distinguished researchers as well as professors in this area. So we will send you the announcement soon. Thank you and have a nice day.